So in the following uh, number of videos, I want to discuss the question of when do you stop a mathematical experiment? And of course, this is not a reasonable question. Uh, it's not a question that can be answered within the realm of mathematics. But of course, we still need to somehow think about these things, because if we're starting on a mathematical experiment looking for a counterexample, or trying to find some sort of behavior, then we need to think about, um, because almost always there is an infinite number of cases to look at, so we will not be able to look at everything. But then when is it reasonable to stop and say, okay, my experiment supported this hypothesis? So of course we're not so stupid that we go out and say, uh, I didn't find any counterexamples, so the statement is true. But when is it reasonable to say that the experiment somehow supports a conjecture, or at least sort of makes it interesting to look closer? And there's sort of two problems here that are both, I guess, sociological rather than mathematical or scientific. So one is that when you're doing a mathematical experiment, there's a tendency that you have this feeling that you just need to do a little bit more than you get to the result that you're looking at. So the famous experimental mathematician D.H. Leamer had this thing he said, when happiness is always just around the corner when you're doing experiments. And this is a feeling I know very well from my own experiments. You always feel that, okay, I just need this. If I can just speed it up slightly so I get a little bit more information out, then I'll be done, then I'll have something conclusive. But that is usually not the case. So there's a danger that you get caught up in trying to um, get to the next step, even though of course you know that there is no last step. The other thing is, you need to somehow balance the amount of computation that you put in with what you do with an observation. And we have in the book this table, which is just a recommendation, but this is one that I go by myself. So if you want to tell somebody about an experiment that you did about some infinite universe, then I would say don't tell anybody unless you've spent 5 hours. Um, so I mean, after 5 hours, then maybe it's serious enough that you can tell your friends. Spend 50 hours if you want to tell a teacher or a colleague. That doesn't apply in this course, right? We don't have 50 hours. But if you were to do something outside this course, uh, make sure to spend a couple of days of computing before you tell a colleague or a fellow student or a teacher. And if you want to put it in a paper or a thesis or something like that, spend 500 hours. Because, I mean, so what we're trying to do here is to balance the amount of time that goes into an experiment with how embarrassing it is to come back and say, oh, there was this counterexample, I just didn't find it because I didn't run my program long enough. So that's the idea here. That's of course not a very scientific approach, and I think this is true for all of this. It's almost impossible to tell, and from the beginning, and this is exactly what these examples will show, that sometimes you were when people made various conjectures, they were just on the boundary of finding a counterexample. Other times, there's a very long way until a certain question has been resolved. So the examples I have is 5 conjectures, 5 plus. So one of Fermat, uh, slightly altered, one of Euler, one of Polya, and then 2 or 3 of Goldbach. So let's start with Fermat. So as we've already discussed, Fermat's conjecture that numbers of the form 2 to the 2 to the n plus 1 were all primes has been refuted by Euler, but there's a case which was open somewhat longer, namely what happens if you have numbers that are iterated powers of 2. So 2 to the 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 2, certain number of times, plus 1, is that always a prime? And you can define this recursively by saying, okay, I start with a1 is 1, then a2 is 2 to the 1, so that's 2. Then a3 is 2 to the 2, so that's 4. Then a4 is 2 to the 4, so that's 16. Then you get 2 to the 16th, which is 256. Then you get 2 to the 256. No, 2 to the 56 is 2 to the 16 is 65,636, and so you have that power, and you keep on going. So of course these numbers grow very, very rapidly, and so you may conjecture that they're all primes, and in fact the numbers that were known to Fermat to be primes cover all the numbers we've talked about until the last one that I had problems computing. And so that's one conjecture. The other one we've also touched upon already. That's one by Euler, saying that if you have a number of nth powers which sum up to another nth power, then the number of factors has to be bigger than the power, unless we're down to 2. So for a sum of nth powers to be an nth power, it has either only one summand or at least n. So this, as we've talked about already, this was known to Euler to be true if n was 2 or 3. But more generally, this was only a conjecture, and this was disproved, as we've seen in a paper of Lander and Parkins. But I want to return to this question more systematically now. The conjecture of Goldbach, one of them, is that every even number bigger than or equal to 4 is the sum of two primes. So that's a very reasonable thing to ask. Also conjectured by Goldbach, which was sort of of the same nature, is that every odd number bigger than or equal to 5 is the sum of a prime and 2 times a square. And finally, the conjecture of Polya has to do with a so-called Liouville function. So the idea is that if you have a number n, you can prime factor it, and then you look at the number of prime factors counted with multiplicity. And then you say that lambda of n is -1 if there's an odd number of prime factors, and it's +1 if there's an even number of prime factors. There's something called omega for the number of prime factors, so essentially lambda of n is -1 to omega of n. And then what you can do is you can add these numbers up, plus or -1, and see what happens. And if you do this for a little while, you keep on getting negative, non-positive n numbers out. And Polya conjectured that L of n remains non-positive all the way out to infinity. So I'm not really motivating any of these conjectures. I mean, you can see that they're sort of natural questions to ask, but some of them actually have very important implications other places in mathematics. So something like Goldbach's conjecture, I don't really think is important for anything, but Polya's conjecture, if it had been true, would have some implications for the Riemann conjecture, which of course does Riemann hypothesis, which doesn't get much more important than that. So we sort of have a variety of importance in sort of mainstream math with these experimental approaches, but that's not really so important for me right here. So when the conjecture was made, of course, Fermat didn't look at the 2 to the 2 to the 2 to the case, but that was okay for n less or equal to 4. Euler, we don't know how much he tried that, but he knew that it was okay for n equals 3. Goldbach is said to have tested until 10,000. I think he claims so in a letter. And the other one was tested, I don't think by himself, but by somebody else, until roughly 2500. And the question of Polya was actually it's not so easy to compute these numbers and check them up to 20,000, but there was sort of a business, a whole sort of industry around this, making efficient computations of the Liouville function um, that that made it possible pre-computer to test this up to something like 20,000. So these are all conjectures that go back to before the existence of computers. Polya is the youngest one, and that was, I think, about 100 years ago. Okay, so what do we know today? Well, what we know today is that Fermat is even the refined Fermat conjecture is false. It's actually false at the case that I was just mentioning, where n equals 5, so just the next step. Euler is false at n equals 4. I've shown you the relatively easy counterexample with n equals 5, but there's also one with n equals 4. The Goldbach conjecture concerning even numbers being sums of primes is open. It has been tested to something like 10 to the 18. The other Goldbach conjecture is false, and there are fairly small counterexamples at 5,777 is the smallest one. And the one by Polya is also false, but there you would have to wait for a long time. It's almost 906 million 180,359 is the first time this number comes up and gets to be positive. So you can sort of see that there's a big difference between how far you need to go. Of course, the Fermat thing, I mean, n equals 5 makes it look small, but of course, if it's 2 to the 2 to the 2 to the 2 to the 5 times, then you see that these are big numbers. So what I intend to do is to show you a little bit about how these experiments would take place, would sort of pan out in Maple, and I think I can just do the first one with regards to the powers of 2 plus 1. So before the number we're looking at is 2 to the 2 to the 16 plus 1. And before I hit enter here, I want you to look down, down here where it says memory, where you can see that my computer now has 4.18 megabytes reserved. And when I hit return, nothing happens, but you can see I've now defined this very big number, which has almost 20,000 digits, starting, so Maple will perform what's called elision and not write the middle digits, but it's a big number, right? So in fact, you can prove, this goes back to Euler, that if you want to look for numbers dividing a number of this form, it's a good idea to look at numbers of the form odd number times 2 to the r plus 1, where r is a relatively big number. And so you can sort of say that, I mean, there's a theorem saying that if a number of this form divides, I mean, any odd number can be written like this, but if you make some extra assumptions on the power of 2 and so on, you get led to some elements, so to some numbers that would have to have a special form to divide a number of this form. And then you could just go through them. There's not that many, and in fact, if I press return here, I've sort of run through the examples that you would want to look at, and here's a number that actually divides that number. And the thing I want you to notice before we move on to the next video is that now the memory of Maple on my computer is up to 36 megabytes. And that's simply because this number is so huge that in order to make the divisions, you have to put in a very big, you have to reserve a lot of space to keep this computation going.